everyone. So I'm Wenjun from Yale. I know it's been a long morning, so I'll try to keep it brief and hopefully interesting. And then also, some of you may know me before as more of a wireless person, but actually I found myself being one of the few people talking about non-wireless topic today. Okay, so here are lots of emerging pictures of emerging applications. So essentially these days you have your phones and IoT devices, whatever. Well, what they're actually doing is essentially take pictures, sense the environment, interact with the environment, and then provide some kind of decisions or information for you. So, one way or another, essentially they're all morphing into some kind of cognitive assistance or just generally speaking, AI assistant kind of applications. Now, the main thing then is because they need to sense the environment and process a lot of data, then generate some useful information and all that stuff. They tend to be very computation intensive, but also they tend to be very interactive. So there's also a lot of implicit, one way or another, latency requirement as well. So of course now originally say Siri and the like offload everything to the cloud to take care of the computing part. But of course, that's not good enough. So, and I'm going to be brief here. So basically, as we already know, there's all this talk about, okay, cloud is too far away. We need to really get back to the ground level, right? So there's been all this talk about mobile edge computing. Roughly speaking, is some kind of intermediary between what you think of as cloud, like somewhat remote, or the device. And in fact, the notion of edge is actually, I don't think there's actually even consensus. Some people think of the device as the edge. Some people think of the next level up as edge. But it doesn't matter here. So the point here is that really we want something that's near the device, that's more powerful, and then that can take care of lots of things. But then, again, this term has been around for a long time. But if you think about it, or when I look around, there's actually not much consensus about what it really means, what you should do, and what's missing here. There's all this supposedly all this interest about researching mobile edge computing, but when I was asking my students to look around, they didn't know what to look for, and we're just thinking about ideas. So essentially, after looking around for a while, we've come down to this overall conclusion that, well, roughly speaking, we need some kind of runtime for edge, server or cloud or whatever you call it. Now, okay, this is a very generic term as well because in some sense, what's happening here is that it does two things. One is it's essentially like an intermediary between device and cloud. Now, I have dashed lines here because this cloud may or may not be needed. In some sense, if you want to optimize for latency, you want to take care of everything as close to device as possible. But that's actually an interesting service purpose as well because in some sense, the device side is also is generating a lot of data. Then some of them may need to be transferred to the cloud. So the edge side can actually be a service, like some kind of proxy for the cloud as well. So that's why it's very useful intermediary to have both sides. Now, this also, so then in terms of functionality, if you think about it, well, it does a bunch of things, right? So it may process data briefly. It does everything the device needs to do, so like we don't need the cloud anymore. But also, so more specifically, you can think of this as, so we talk about offloading and there's acceleration or whatever. So if there's something that can go into runtime as either a general programming model or some kind of generic libraries for a bunch of different applications, that sounds very useful. And then for the cloud side, well, as I just said, there's all this data generated from all these devices. You don't want to send everything back to the cloud. Maybe you need to do some sampling, maybe some other pre-processing, some kind of, actually it may or may not be the right term because that means different things to different people as well. But essentially, you want to some kind of source through some of data and then see if anything needs to be sent out further. So this is an overall idea we have here. But again, this is being a bit vague because we're still trying to figure out what that needs to be there in this cloud. In some sense, you can think of this as providing a bunch of services. So either for either side, I already highlighted a little bit there. Or you can think of it as a bunch of libraries. So you might have some common scheduling functionality that needs to be done for, say, split computation between these three tiers. So that's something that may become some kind of middleware essentially. So just to give you some idea, this is actually an early work we did last year. You can think of this as one piece of the whole thing. So the name, as the name suggests, we call this fully cache. So as the name suggests, it has something to do with caching and reusing results. So roughly speaking, there are a bunch of algorithms that does this and also a system to actually implement that. So I'll give you some idea what this actually means. Let me step back a little bit. So if we go back to the apps I saw the show a few slides ago, right? So let's say here one example where Google Lens, for example, tries to, and also they have applications that I think it's called visual positioning system and the like, which essentially is built on, you have a camera maybe on the phone that basically sort of look around. That's almost like a process for your own eye. I mean, not as comprehensive, but it's kind of the idea. And then the camera takes lots of pictures and then maybe recognize objects in the picture and then tell you something about something useful. So for example, let's just say this is some kind of tourist assistant kind of guidance app or some kind of navigation app, right? So let's say these are actually pictures of the student library on your campus. So now what happens here is that because this is a major landmark on the campus, people tend to go there, and then essentially in this kind of touristy navigation scenario, what will happen is that you will have all these different people going somewhere near there. The camera view will see this building there, and then essentially if they run the same app, the camera or the processing results will say, okay, you're actually staring at student library, and then maybe you want to go in there or turn left or do something, right? And the rest actually doesn't matter here. So the point here is that now if you look at these three pictures, think about what's really needs to be done on these applications, right? So essentially they need to take pictures of the library, and then in all these pictures, they need to recognize, okay, this is actually student library, and then you do something else with it. Okay. Now, in all these cases, basically that means that the image recognition step or classification is actually one of the main computation steps for this particular application, right? So now, if you think about it, so let's say we actually took some examples from some street corner and then take pictures from Google Street View, right? And then if you follow this example, in fact, if you up to this amount, like 82% of the images around the same intersection will essentially give you the same kind of recognition results because they are usually about the same landmark or street sign, like stop sign or like street name and some other major point of interest, right? So then, of course, the natural thing is, okay, there's actually a lot of redundancy from all these pictures taken on different cameras because they're running on the same device, different devices with similar apps, right? So it seems kind of redundant to have all these devices go through the same application, the same computation pipeline, but essentially giving the same results. So a very natural question is, okay, so this amount of correlation, can we do something with it, right? Now, again, it sounds kind of intuitive that you want to reuse any previous result that may already be there, but it's actually not so trivial. So what we're actually saying here is that essentially what this requires is something called approximate condition reuse. So if you look at these two pictures, right, they're actually not the same pictures. But what's important, what's useful for us is that they are all pictures about student library. So as long as you recognize somehow these are the same, so essentially if you recognize they are somehow equivalent semantically in that sense, you can actually reuse the results here. So for example, let's say we have this image, what is from that picture, from that phone, you will recognize, okay, this is student library. And then we can actually cache the results here, the picture and also the results. And then when you get a new picture along, if you can recognize these images, sort of, I mean, it's not the same, but sort of equivalent in that sense. And then you can say, okay, we don't need to go through the usual recognition library pipeline, and then just say this is enough. Then that will actually be very helpful for us, right? Especially if you go back to the previous number, if really 5 out of 6, kind of workloads are actually the same, then you can actually skip a lot of that potentially. So the rough idea, what we designed here is that basically, first of all, you have input data, so it's some kind of cache pipeline, but with more algorithms to deal with it specifically from this approximation part. So essentially, when you have input data, you first look up any potential record that's already cached with similar input. So this is actually very important here because a lot of challenge goes into how to detect similarity, and I think an index is very, very appropriate so that you can search very quickly. So we actually have some algorithm here. I'm not going to go through. Actually, sorry, I'm getting ahead of myself. And then the next step is, once you found a similar input, now potentially there are a few different similar inputs. So we need to pick one, and they may give a different result, they may give the same results. So potentially we need to pick one out of whatever results from this side, and then see whether we actually have one that will be appropriate for these purposes. So for these two parts, we actually designed some algorithms. For the first part, we actually had a version of adaptive locality sensitive hashing to deal with the similarity and making a very, very effective indexing structure and searching very fast and also very accurate as far as possible. And then for the second part, we had a version of a reverse version of the k-nearest neighbor algorithm to actually figure out what's the right way to make use of the current results for the first step. Okay, so I'm not going to detail the details algorithm here actually are not relevant to this talk per se. I'm just going to, it's just part of the system. So in terms of system implication, basically what happened here is that we built this as part of the offloading runtime. Now in this picture, it says native processing library because this is intentionally vague. It could be either on a device or it could be on offloading remotely. It doesn't really matter. It's basically the point is it's actually more or less transparent to the application, just sort of intersteps when you start to call offloading. Then we kind of see you can actually skip a step here. Yeah, and then so basically, if you have reusable results, you have to go. Sorry, if you don't have reusable results, you have to go through the usual offloading pipeline. Otherwise, you can essentially bypass that what the previous figure showed. And then in terms of the storage part, because we need to keep track of results, and also because we said one of the interesting point about this scenario is that you actually essentially have multiple devices running the same app and near the same location. So this is where ideally you can actually have an edge cache that saves all these results and sort of share between different devices. That's why we have essentially some kind of edge kind of cache here, and then they can be sort of synchronized between the local cache. So you can reuse either locally and then remotely. And then we have some algorithms to essentially improve the hit rate on the remote and also optimize for the synchronization part as well. Okay, so just some idea of the results. So this is how we actually did the experiment. Basically, we had this a desktop as the edge server, and then just typical a phone basically. There's not many other devices we can really play with in that sense. So we tried a few different application categories. So especially for the most part, it's basically vision-based and also speech-based. And then so for each of these, we basically use some standard data sets. Now, I'll get back to this in a minute, but part of the point here is that we're not trying to evaluate how often these things happen because we don't have real data to show how often you actually do have correlation stuff. We're trying to use this to say if you have correlation, to what extent can we actually make use of that? So this is actually where using standard data is actually help us because we took some video feeds as well. So let's say walking around campus or maybe walking around grocery store, and then you can see if you want to recognize a lot of objects along this trajectory, how many frames are actually very similar because of the spatial temporal correlation. And then what's interesting about using standard data sets is that the data sets actually don't have the images in the data sets actually don't have the same spatial temporal correlation as in a video. So in theory, this should be more, not just in theory, actually we also show in results, using these actually are the more demanding situation compared to what you might see in the real video feeds here. So anyway, so this is just a setup. There are lots of results just to give you some idea, because essentially keep in mind we're trying to say, given particular kind of data set with a certain amount of correlation, how much can you make use of, and then how does that accelerate your results, right? So in that context, basically what we can show here is that if we have this data set to emulate these three applications, then essentially, so without and with means this is without our cache and this is with our cache, and then this is the energy consumption also. How much? So because sometimes because this is approximate, you may actually pick the wrong results as well. So occasionally you actually do get the wrong results back. So you also imagine accuracy loss on that. This is actually relative. It's not absolute accuracy loss. So basically, you can see using reviews, depending on the exact data sets, you can actually accelerate by 3-4 times just by doing simple lookups and stuff. And then that also saves energy back a bit, especially for mobile devices, right? Okay, so this is just a very concrete example of what we actually did, and we think this can be part of the whole piece of the whole runtime of things. So, so basically, this brings me to what we can make use of from Cosmos. And actually, I want to go back to this slide a little bit again. So as I just said, I already explained the data sets here, and this is how we decided to do the experiment. Because when we first started doing the work, when we talk to people say, oh yeah, it sounds intuitive, but can you show to what extent this correlation stuff? I mean, this is stuff we cannot show because unless you do real measurements, from some real applications, you don't have the actual real data, and it's actually very difficult to get this kind of data as well because some of these applications are still coming up. They are not widely deployed necessarily, but when you explain this, everyone says, oh yeah, it sounds kind of intuitive. So it's becoming a chicken and egg problem a little bit. But then there's also this part. So for that particular work, we don't need to worry too much about scalability or latency and everything. So the main thing is to show you can run something on the edge and then the coordination is all work out. But then the more interesting question is, okay, if you think back to the scenario I mentioned at the beginning, right? So let's say when it's a navigation app or some kind of speech assistant, it's more useful in some kind of urban environment where, near a real landmark or speech especially, it'll be interesting to go to some place where with a lot more ambient noise and stuff. So you can actually start to get some idea of what kind of real scenario may actually benefit from these cases. And also for this, so again, this is a very simple architecture. Now, going back to what I said earlier, what's not known essentially right now is what's the right edge architecture. Maybe there's no right architecture, but there are a few different types depending on the scenarios and also what you really need and who's deploying that, who's managing that and stuff. So essentially, for our point of view, it would be nice to have some more comprehensive edge either a single server or cluster kind of setup. So whether it's a matter of different computation power, different processing capability, different latency setup for end devices, and maybe even there might even be a pricing or management consideration depending on what's available and what else is there, right? And also, but for experimental point of view, I kind of don't know what control we can have because typically when you want to share machines between experimenters, there has to be some kind of VM-based control. But we might actually need like a cluster of VMs or something. So I'm not too sure what we actually, in some way, I don't even know what we need here because it depends on what we can get. Okay. And of course, this is also, I think someone else also mentioned this earlier. So in some sense, what we really want to showcase all these ideas is if there are realistic application, both in terms of user mobility, network access pattern, basically the more dynamic situation you might see in a real urban environment, different apps and stuff. And then based on that, we can actually say, okay, we have these ideas. In some real setting, they can really give you, say, X% benefit and stuff like that. I mean, this depends on how the test bed can be set up and what else is there. And then, okay, so this part is maybe easy, maybe not, depending on, I mean, we can always, wherever your survey is, we can always send it to somewhere else as a class. But then it's interesting to see whether we actually complete the whole loop. Okay, so that's all I have. So I'm happy to take questions.